Welcome to Lesson 9A, Introduction to Laminar Flow Solutions. In this lesson, I'll list several examples of laminar flows that can be solved analytically. I'll review the differential equations of motion, including the Boussinesq approximation. I'll show a step-by-step procedure to solve these problems, and then I'll do an example. First, I'll list some examples of laminar flows that we can solve analytically. Steady flow between parallel plates, also called couette flow. Steady pipe flow, also called Poiseuille flow. Flow between circular cylinders with any two rotation rates. Axial flow in an annulus. A cylinder rotating in an infinite fluid. A falling film on an inclined wall. Gravity-induced flow between two vertical plates, etc. There are several other analytical solutions available, but you can probably count them with your fingers and toes combined. Now let's review the differential equations for nearly incompressible laminar flow. We had derived these in a previous lesson, where we assume Newtonian fluid with constant properties, laminar flow, nearly incompressible, which is typically either an incompressible liquid or an ideal gas at very low Mach numbers. We'll sometimes apply the Boussinesq approximation, where, as you recall, density is constant except in the buoyancy or the gravity term. This is our equation for density, where alpha is the thermal expansion coefficient. Rho naught is the reference density at a reference temperature. With the Boussinesq approximation, temperature varies only slightly, so that we have buoyancy, but density is constant everywhere else in the equations, namely rho naught. We also assume alpha is constant. With all these approximations, we have 5 unknowns: pressure, 3 components of velocity, and temperature. Thus we need 5 equations. We have continuity, which is a scalar, linear momentum, which is a vector, and one of our forms of energy equation, which is a scalar. Thus we have 5 equations and 5 unknowns. We also need boundary conditions, and if the problem is simple enough, we can solve it analytically. If not, we have to use numerical methods or computational fluid dynamics. Here I summarize the differential equations of motion from previous lessons. In tensor notation, conservation of mass. Linear momentum, here's the Boussinesq approximation term, or we can divide everywhere by rho naught and introduce kinematic viscosity. As you recall, we had several forms of the conservation of energy equation. For a nearly incompressible liquid, we approximate density as constant, but we do include the viscous dissipation term, which, as we'll see, alters the temperature profile. If we have an ideal gas at very low Mach number, it turns out that the viscous dissipation term is negligible. We can also use kappa, the thermal diffusivity, which is a combination of rho naught Cp and K, as shown in this equation. I point out that when we're using the Boussinesq approximation, T appears in the momentum equation, which couples energy and momentum. In some cases, we have to solve all 3 of the equations, mass, momentum, and energy, simultaneously. In some simpler cases, continuity and momentum are uncoupled from energy. I also write out the vorticity equation, which is not one of the 5 primary equations, but we will sometimes find it useful. I'll quickly go over a general solution technique, and then we'll do an example. First, you expand out the differential equations. You list all the boundary conditions, simplify the equations as much as possible, solve for the unknowns, and then apply the boundary conditions. Here's the example I'll do: steady incompressible flow between infinite parallel plates. I note that in lesson 4b, we solved for couette flow, which is a simplification of this problem. Here we allow pressure to change with x, but the geometry is the same as that of couette flow, namely a top plate that's moving, a bottom plate that's stationary. Gravity acts down in the negative y direction. These fluid properties are considered constant, but we impose a pressure gradient del P del X. These are our assumptions and approximations. The walls are infinitely long, horizontal, and parallel. We already mentioned these. We'll assume incompressible flow with constant properties, but we will account for viscous dissipation when we examine the temperature. The imposed pressure gradient is typically negative, so that we get a forced flow in the x direction, pressure decreasing as we go downstream. Flow is steady, 2-dimensional, with gravity acting only in the negative y direction. The flow is also fully developed, both in velocity and temperature, and we let heat transfer be whatever it needs to be to keep temperature equal to T0 at the bottom and T1 at the top. We want to calculate the velocity, pressure, and temperature fields in this flow. We start with the continuity equation in Cartesian coordinates, and we cross off terms that go to 0 by our approximations and assumptions. Del U del X is 0 because the flow is fully developed. Del W del Z is 0 because the flow is 2D. Thus, del V del Y is the only remaining term, which implies that V is not a function of Y. But we know from our approximations and assumptions that V is not a function of X, since it's fully developed, or Z, since it's two-dimensional, or time, since it's steady. Therefore, V is not a function of anything. In other words, V must be a constant. We can apply one of our boundary conditions. At y equals 0, V equals 0, since there's no flow through the bottom wall. So if it's 0 there, it has to be 0 everywhere. So we have our first solution, that V is 0 everywhere. Now let's apply the y momentum equation. Again, in Cartesian coordinates, we write it out like this, but V equals 0, which eliminates the first and final terms. Gy is negative g, since gravity is acting down in the negative y direction. Thus, del P del Y is minus rho g, which we can integrate, noting that P is a function of both x and y. So the integration gives negative rho g y plus some function of x, not a constant, since this is a partial integration. I'm going to call this equation 1. By the way, this is the hydrostatic component of pressure. Pressure increases linearly downward, just as it would in hydrostatics. The f of x represents the dynamic component due to the flow. Now let's apply the x momentum equation. I'll write out all the terms. And again, we cross off some terms. The flow is steady. It's fully developed. From continuity, V is 0. It's 2D. There's no gravity in the x direction. It's fully developed. And again, 2D. So this long equation reduces to only two terms, del P del X equal mu d squared U dy squared, where I use d instead of del, since U is only a function of y. It's not a function of x because it's fully developed. It's not a function of z, since it's 2D, and it's not a function of time, since it's steady. So the partial derivatives can turn into total derivatives. But we kept del's here because p is a function of both x and y. Let's call this equation 2. Let's go back to equation 1 and take the x derivative, where this term does not contribute, and this one gives f prime of x. Well, f prime of x is a function of x only. Therefore, del p del x, on the left side of the equation, must also be a function of x only. But now we have a problem. Del p del x is a function of x only, but here del p del x is a function of y only. How can this be? Equating del p del x, we have a function of x only equal to a function of y only. This is possible only if both sides are a constant. In this case, del p del x is the function of x and the function of y. Thus, we conclude that del p del x must be a constant, which means that p is at most a linear function of x. Keep in mind that p is a function of both x and y, but its functional relationship to x is at most linear. Now let's go back to our equation 1, which we differentiated, but del p del x we now know is a constant, where the constant is del p del x. So integrating this with respect to x, f of x equal x times the constant del p del x plus some other constant, not a function of the other variables, but a constant since f is a function only of x. This is a total integration rather than a partial integration. Finally then, our equation for pressure becomes negative rho gy plus f of x, which is given here, x del p del x, plus a constant. I'll call this equation 3, and you may be unsettled by the fact that del p del x appears in this equation for pressure. But keep in mind that del p del x is the imposed constant pressure gradient. In other words, we're applying a pressure gradient in the x direction to push the flow through. Graphically, p varies linearly with x. The absolute value of pressure makes no difference. No matter what the initial pressure, it will decay linearly with x. Physically, the whole channel can be pressurized, but the flow is not affected. We have the same pressure gradient, regardless of the absolute level of this pressure. Now that we have pressure, let's go back to equation 2, where we now know that the right-hand side is a constant. This can be easily integrated twice. Integrating once with respect to y, we add constant c1, and when we integrate again, we get u equal 1 over 2 mu del p del xy squared plus c1y plus some other constant c2. Note that we add constants here since these are total integrations, not partial integrations. This is our solution, and now we apply boundary conditions to find constants c1 and c2. Namely, at y equals 0, u equals 0, the bottom wall is stationary, and since y equals 0 here and u equals 0, c2 must be 0. At the top plate where y equals 2b, u is capital U since that plate is moving. Plugging in capital U for u and 2b for y in both of these places, and knowing that c2 equals 0, we can solve for c1. A little bit of algebra yields c1 is u over 2b minus b over mu del p del x. So finally, u becomes y capital U over 2b minus y over 2 mu del p del x times the quantity 2b minus y. I'll call this equation 4, which is our final solution for u as a function of y. If you look back at our previous notes from lesson 4b, this part of the solution is couette flow. This part of the solution we'll call plane or planar Poiseuille flow. In other words, if del p del x is 0, there's no forced pressure gradient, we have couette flow. And if the top plate is stationary, we have a parabolic profile that we call plane Poiseuille flow, which is kind of a two-dimensional version of pipe flow. We can imagine superposing these two components of flow to get the more general case of equation 4, which will be a combination of couette flow and Poiseuille flow, so that the final velocity profile for u of y looks something like I sketch here, where u goes from 0 to capital U, and there's a forced pressure gradient that pushes the middle part of the flow downstream.
Sir, how can superposition work when the equations are nonlinear?
Good question, Jack. In general, that's true, but if you go back to the momentum equation, here in vector notation, the whole left-hand side term has dropped out, and this is the nonlinear term. So because of the nature of this problem, the governing equations are actually linear, and that's why superposition works in this case.
Thank you, sir.
In general, the Navier-Stokes equations cannot be superposed because they are nonlinear. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.